So today we're going to talk about the sum and difference formulas for trig. So let's go ahead and write out the formulas. We will have sine of u plus v is sine of u cosine v. Let me get a new pen here. Plus cosine u sine of v. Actually, I'm going to change this symbol a little bit. Instead of plus, we're going to make it a plus minus. So we've seen plus minus a little bit this semester. It comes up whenever we got to apply square roots. In formulas, it's a little bit different. So the plus minus means plus or minus. But in problem solving, like when we use square roots, it usually means or as in both. So we usually have two sets of solutions or two answers in that case. In this case, it essentially means we have two different formulas. And so what do we mean by two different formulas sort of compactly written in terms of one? You just have to be careful that whenever you see these symbols, plus minus, you always want to choose the same one based on its relative position. In other words, we want to choose either the top symbol everywhere or the bottom symbol everywhere. So for example, if we have a sum of angles, u plus v, means top symbol here is the plus, we use the top symbol here as the plus. And conversely, if we have u minus v, bottom symbol is the minus, we want the bottom symbol here as well. So it would be a minus in the formula. So you do want to be careful with that because in cosine and in tangent, sometimes it switches. So cosine of u plus or minus v is going to be cosine of u cosine of v minus plus sine u sine v. So this means that if I have a sum of angles, u plus v inside the argument of cosine, that's the top symbol, means we got to use the top symbol here. It's a minus. So the sign switches in the cosine formula. And likewise for tangent, tangent has a little bit of both. So the tangent formula is going to be tangent u plus or minus tangent of v over 1 minus plus tangent of u tangent of v. So essentially it means that if we have a sum inside the argument of a tangent, then we pick a sum, the top symbol in the numerator, but a negative minus sign in the denominator. So the symbol switches in the denominator there. So those are our formulas. Go ahead and keep those handy. And I'll try to bring them up when I can for these problems. But we will be giving you these formulas on tests and quizzes. So you don't have to memorize them, just understand how to use them. It is a little bit more of a complicated formula now, since we have these plus minuses and minus pluses going around. And let's go ahead and try to put some of these to use. So let's go ahead and try to compute sine of pi over 12. So this is the weird thing about the sum and difference formulas is we actually aren't getting many new angles we can compute with them, at least from our initial building blocks. So remember, we have our building blocks are the angles we like and can compute pi over 2, pi over 3, pi over 4, pi over 6, along with any multiples of those we can compute trig functions on. And then what did we do when we learned the half angle identities? We realized, okay, now I can expand that. And out of these building blocks, I can now compute trig functions on a broader set of angles, namely angles with a denominator of 8, so pi over 8, and pi over 12, when we cut those two in half. And then again, any scalar multiples of those, or any integer multiples of those. So pi over 12, we could actually use a half angle formula if we wanted to, but for the sake of using our sum and difference formulas, let's figure out, well, where does this come about? So the only thing that's going to be different with sum and difference formulas is, well, now we got to find a common denominator is really what you want to think about. So in WebAssign, they might have these problems broken down where you first have to write pi over 12 as a sum or a difference of some angles in our building block repertoire. And so that's going to be our first goal. And so what you want to do is, well, if we want a denominator of 12, you really just think which pair of angles will have a common denominator of 12. And once you find that pair, you can essentially use those. You just got to figure out what the numerators need to be and whether or not you are adding or subtracting. So when you look at pairs of these, well, 2 and 3 have a common denominator of 6, so we actually don't need that since we already have 6. 3 and 4, common denominator of 12. Likewise, 4 and 6. So either 3 and 4 will work, or 4 and 6. Let's go ahead and use 3 and 4 since those are smaller. It's going to be a little bit easier in terms of the numbers we get, but 4 and 6 would work just as well. And so what you have to get good at with a lot of these is figuring out, well, what scalar multiples of those will give us pi over 12. And you actually have a little bit of freedom to guess and check here a bit. Really what's going to happen in this process is if we tried to find a common denominator, we'd multiply this term by 4 over 4. This term by 3 over 3. Then if you look at the numerators, I'm going to have 4a plus 3b equals 1. These a and b are the scalar multiples. It's essentially the numerator here. And we need to figure out what integers should go in the numerator here so that it'll, when I add the fractions, we'll get pi over 12. And we're essentially reverse engineering this problem solving process of just saying, well, if I tried to find a common denominator, that's what the expression would look like. And that means I would really have 4 times a plus 3 times b equals 1. And a little bit of guess and check here. There's not necessarily a definitive solution. I would always try to pick easy numbers, pick low numbers. So hopefully you can kind of see that if I have actually 4 minus 3, that gives us 1. So you can just pick a as 1 and b as negative 1. In other words, what we're doing is recognizing that pi over 3 minus pi over 4. So that's just plugging in a as 1, b is negative 1. And if we try to find a common denominator, we get pi over 12. It gets a little harder, like if it were 5 pi over 12 or 7 pi over 12. We still want, a 3 and a 4 in our denominator would work. But then the a's and b's, the scalar multiples would be different. We might want like 2 pi over 3 and 1 pi over 4, something like that. You'd have to work it out. So a little bit of work from the initial setup, but now the computation actually becomes a little bit easier in some ways than the half angle formulas. So sine of pi over 12, we're just going to write as sine of pi over 3 minus pi over 4. And now we can use the formula that's going to be sine pi over 3 cosine pi over 4. We have a minus there. So a minus in the formula is the bottom symbol, which means we want to use the bottom symbol throughout. So bottom symbol there is a minus. Minus, now we've got cosine pi over 3 sine of pi over 4. And now we can evaluate all those. So sine of pi over 3, draw your reference triangles if you need to. Sine of pi over 3 is going to give us square root 3 over 2. Cosine pi over 4, it's going to give us square root 2 over 2. Or 1 over square root of 2, whichever way you want. I'm going to use square root of 2 over 2 since we're multiplying things in fractions. It's going to be a little nicer if we don't have an extra square root in the denominator. And we can combine our square roots of the numerator when we multiply. We've now got cosine of pi over 3, gives us 1/2, and sine of pi over 4, root 2 over 2. So evaluate all those, and now we just multiply straight across for fractions. So square root of 3 times square root of 2 gives us root 6, minus the square root of 2, and then both of them, nicely enough, have the same denominator. So it'll just be 4. And this works out fairly commonly with these sum and difference identities, that the denominators of each term should be the same. And so not too bad to just multiply and then add or subtract in the numerator. The other nice thing about the sum and difference formulas is there's no like fractions within fractions. There's no square roots within square roots. So if we remember how we did the half angle formula for that, it's often a square root, and then underneath that square root, you might have extra square root terms, and often a fraction, then divided by another fraction. So sometimes the algebra on those can get a little hairy, whereas the algebra with the sum and difference formulas, most of the time is pretty straightforward, at least for sine and cosine. Tangent, a little bit more algebra involved, more arithmetic. So as long as you start to get good, of course, the work with the sum and difference identities can be actually identifying what angles you need to add or subtract to get the angle you're trying to evaluate. So for me, I think that's a little straightforward, and it's good practice for you guys too. This is kind of like a linear sums, that if anyone has to take linear algebra, you'll be doing stuff like this, but also good stuff, good problem solving techniques that appear here and there in calculus as well. So once you get good at that, fairly straightforward, and then the computations are fairly easy with these formulas. Let's go ahead and check out one more. Let's do one simple one of evaluating. Let's use 75 degrees. So sometimes they'll give you the angles they want you to use in the problem statement. Like in the last one I mentioned, we could write pi over 12 in terms of pi over 4s and pi over 6s, and adding and subtracting scalar multiples of those. Sometimes, especially on WebAssign, they might tell you how they want you to break it down as they walk you through some of those problems. So let's say use 75 degrees is 30 plus 45 to evaluate cosine of 75 degrees. So again, we just write the angle sum in the argument. Once I have a sum, we can now break that down in terms of our sum and difference identities. So pull up the cosine formula. First part of the cosine formula says cosine cosine, so cosine of 30 times cosine of 45. And then careful, so the cosine formula, remember, we have a plus in our angle, so top symbol here is a minus. So the cosine formula, the signs switch. So plus there, we'll have a minus sine, so sine 30, sine of 45. And now the rest, just evaluating again. So cosine of 30 degrees is root 3 over 2. Cosine 45 degrees, root 2 over 2. Sine of 30 degrees, 1/2. And sine of 45 degrees, root 2 over 2. Multiplying things out and adding. Once again, we get square root of 6 minus square root of 2 over 4. So these types of expressions will be fairly common, especially with sines and cosines when you're evaluating things that have a denominator of pi over 12. Be very, very careful with these minus signs, though. So multiple choice tests, how are we going to change these answers? Well, we might have this one listed. Well, we should have this one listed for the correct answer. But then we'll also have maybe square root of 6 plus square root of 2. And then maybe square root of 2 minus square root of 6. So these expressions, you'll probably start to see some similarities in the answers you get with these, but with some slight variations, right? If this were a minus here, then that would have turned this sign into a plus. So you could see pluses there, but of course you want to be careful because we'll also put those as distractors on multiple choice tests. So always double check those minus signs, again, because there's no partial credit on these multiple choice exams. So that one little mistake costs you the whole problem. Started to get into a little bit harder stuff now. So one thing we can do is verify certain identities, or let's see, what does it say? Sometimes the problem statements can say multiple things. Sometimes it'll just say simplify or reduce. We call these reduction formulas. Okay. Reduction, reduce. Or really, write as trig functions of theta. And what we want to simplify is cosine of pi over 2 minus theta. So by writing it as a function of only theta, right now we have a function evaluated on pi over 2 minus theta. So we want an expression that only involves trig functions evaluated on theta. So sine theta, cosine theta, tangent theta. We'll go ahead and spell this out in terms of our angle difference formula. So cosine starts off, cosine, cosine. We have a minus here. The sign switches to a plus in this cosine formula. And then sine of pi over 2, sine of theta. Then we evaluate and simplify the terms we can. What is cosine of pi over 2? So remember, pi over 2 should be a straight vertical angle. It's one of these degenerate triangles. So cosine gives us 0. 0 times anything will give us 0. Plus sine of pi over 2 is just 1. So we're just left with sine theta there. And as our answer. So of course, this is just the cofunction identity. Cosine pi over 2 minus theta equals sine theta. We derived it geometrically when we first introduced the identity. And then now this is essentially deriving it formulaically. Okay, so let's get into the little more abstract ones and try to solve these guys. Let's say we are given that sine of u is 4/5. We are given that cosine of v is negative 12 over 13, with u being between 0 and pi over 2, and v being between pi over 2 and pi. We want to find sine of u plus v. So this is similar to some of the first questions we started asking with trig. Just as soon as we introduced it, we were only working with one angle usually. And then if I give you something about sine of this angle and ask you to evaluate other trig functions, you could. So what's more complicated? Well, now, kind of given the same information, except we have two angles. We don't know what the angles are, but we are given abstract information about these angles in terms of certain trig ratios on these angles, as well as the quadrants of the angle. So as with any of these problems, I always like to start off just by drawing the triangles and figuring out all the sides. Our angle U is in the first quadrant with a sine ratio of 4/5. So that third side, use the Pythagorean theorem. Hopefully you guys are getting used to seeing some of these Pythagorean triples though. So that other side's going to be 3. Let's go ahead and label that. That's our U. Our V is in the second quadrant and has a cosine ratio of negative 12 over 13. So again, use the Pythagorean theorem to find that other side. This one's another nice Pythagorean triple. So 13 squared is 169 minus 144 gives us 25. So once you got your triangles, now let's figure out what they're asking. Sine of u plus v. Let's go ahead and write that out in terms of our formula. So we'll have sine u cosine v plus, we'll give this a plus for sine. We'll have cosine u sine v. And now, once we have everything spelled out in terms of evaluating trig functions on u and v, we've also got our triangles. You just have to plug in the numbers. So sine of u was 4/5. So they gave us that one. Cosine of v, they also gave us negative 12 out of 13. But then cosine of u, we've got to look over on our diagram. 3/5. Sine of v then gives us 5 over 13. And then the rest, just the arithmetic. So we'll have minus 48 plus 15 over 65. So let's say we've got as well, let's call this part A. Part B, let's do one for tangent, just for the sake of doing a tangent one. Let's say u minus v. Nice thing about these types of problems, you will see this. Sometimes they'll say, given this information, evaluate, and they'll have maybe multiple parts and sine of u plus v, tangent of u minus v. Nice thing is once we're given information about u and v and have the triangles, we don't have to do that again. We already have that information figured out. So tangent, now all we got to do is plug it in the formula. So tangent of u minus tangent of v divided by 1 plus tangent u times tangent of v. So again, let's pull up that formula. We have a difference inside the argument. So I'm choosing the bottom formula or bottom symbol here, which means I choose the bottom symbol here and the bottom symbol here. So that one's a minus, that one's a plus. And so we had a minus there and a plus there. And then just compute everything. So let's see, tangent of u gives us 4/3. Tangent of v gives us 5 over 12 negative. So we'll be careful with that minus sign. We've got 1 plus 4/3 times negative 5/12. So the rest, just working with the fraction. So 4/3 is going to be 16 over 12 plus a 5. That's our numerator. Denominator here is 36. So 4 times 5 gives us negative 20. And then so 1 is going to be 36 over 36. So 21 over 12. 16 over 36. You could simplify either of those if you wanted, or however you want to do it. If you want to simplify the numerator and denominator first, or you can write it as 21 over 12 times 36 over 16. And then 12 and 36, those will divide and give us a 3 there. And then everything else co-prime. So we're left with 63 over 16. Okay. So nothing much new here. Again, we've seen problems involving some basic information about angles, or some abstract information about angles. Now we just have this extra layer. We've just got a formula to break down in terms of a sum or a difference of angles. But then again, once you do it, if you got your triangles drawn right, it's just computing then after that. Let's try to get in. Let's see, we don't have much time left. Let's try to do 2 more. I want to do one involving inverse trig functions. And then one involving trig equations. So inverse trig, Remember, inverse trig inputs a ratio, and the output is an angle. So let's go ahead and simplify something like this. Now we have a sum of angles inside of a cosine, but of course these angles are given in terms of inverse trig functions. So we want to simplify this. Another problem statement, it might say write as an algebraic expression. And when we say algebraic expression, we mean just involving sum, addition, subtraction, division, square roots, fractions. So no trig functions, essentially. So given something like this, the first thing I'm going to do is look to see if I can simplify and evaluate anything. You don't have to. One step we're going to have to do is use the sum identity. So you can start off by doing that, but recognize that arctangent of 1 we can actually figure out. Namely, which triangle has a tangent ratio of 1? The 45, 45, 90 triangle. So arctangent of 1 we can actually go ahead and simplify, and that's just going to be pi over 4. And now when we write things out in terms of the sum identity, we'll see what else we need to simplify. So cosine, remember, sum inside, sine switches outside the formulas, and we'll have cosine cosine minus sine sine, sine of pi over 4, sine of arc cosine of x. We can simplify the ones with angles pretty easily. So both of those are square root 2 over 2. Now you just got to remember how to simplify trig and inverse trig when they're interacting with each other. So we've got arc cosine of x, which means we have some angle whose cosine ratio is x over 1. The angle is going to be either in the first or second quadrant. Use Pythagorean theorem, find the other side. So square root of 1 minus x squared for that. Now evaluate. So cosine and arc cosine undo each other. We'll be left with just an x there. And then sine of arc cosine will give us square root of 1 minus x squared over 1. So that's our answer there. You can simplify it a little bit more if you wanted to. This isn't necessary, but if you wanted to factor out the square root of 2 over 2, either of those answers would be fine. Okay, so one more. So now we've seen how inverse trig interact with these guys, with these formulas. Let's take a look at solving a trig equation. So we'll say solve 0 to 2 pi. So the harder things about the trig equations were, this plus 2 pi k, and it's going to get thrown off a little bit when we have an argument that isn't just x. And now we're throwing it off even more with having these shifts. So we'll talk more about that on Wednesday, but of course these correspond to horizontal shifts in the function. So how do we solve something like this? Well, our problem-solving process for trig equations, our first step is to isolate the trig functions. If we can have a trig function equal to a number, we can then solve from there. Our problem is that we really want the same argument in the trig functions. We're not going to be able to isolate either of those when they're being added together if they don't have the same argument. So we're going to use these angle sum and angle difference identities to reduce and break those down a little bit. So let's go ahead and start with this term on the left. We have sine 2x, cosine of pi over 4, sine plus plus, but then we'll have cosine 2x, sine of pi over 4. Is that term on the left. Then, so I'm just adding these brackets in just for organization purposes. Since I can't fit all of that in one line, let's go ahead and break down this guy. So our sine of 2x, cosine of pi over 4. Then we get a minus there, so we'll have a minus cosine 2x, sine of pi over 4, and then equals minus 1. So things are better now. Now the trig functions either have 2x as an argument, or they have something we can straight up evaluate. So let's go ahead and do that. Our bracket, square bracket term, we'll have a cosine of pi over 4 is square root 2 over 2. So I'll write square root 2 over 2 times sine of 2x. Likewise over here, sine of pi over 4 is again square root of 2 over 2. Cosine of 2x. Those are the two bracket terms. Plus. And we'll have something similar in the squiggly brackets. So root 2 over 2 sine of 2x minus root 2 over 2 cosine of 2x. So again, I'm just using the brackets there to help organize the writing a little bit, especially since we have to use the formulas twice for two different terms. You do want to be careful with something like this because this is a plus here, right? This could have been a minus. And if it were a minus, that means that would be a minus, and that minus would distribute. So careful with stuff like that. How does it simplify now? Again, we didn't need the brackets, so we're just adding and subtracting everything now. We'll have this term and this term. So root 2 over 2 cosine of 2x minus root 2 over 2 cosine 2x. Those will evaluate to 0. And now what are we left with? We're left with 2 copies of square root 2 over 2 sine of 2x. Those 2's are going to cancel. And now finally, we have isolated a trig function equal to a number. So nothing new, just extra layers, extra computations and tedious things we got to keep track of in terms of these formulas and pluses and minus signs. Now we have to solve it. So we've got negative 1 over square root 2 So sine is negative in quadrants 3 and 4. And then what is our reference angle? So sine has a ratio of 1 over square root of 2 when the reference angle is pi over 4. So our solution now is we find that reference angle in those two quadrants. Quadrant 3, we go 4 pi over 4 plus 1 more, gives us 5 pi over 4. Quadrant 4, we go 8 pi over 4 minus 1. So 7 pi over 4. But it's cyclic, so we got to have these 2 pi k's. And then when we divide everything by 2, the period changes. Those are our general solutions. We want to find our specific solutions. And 0 to 2 pi, so how do we do that? The initial solutions are always good. 5 pi over 8, 7 pi over 8. And then what do we want to do? I want to just increment k. So if k is 1, we are adding pi, 8 pi over 8, to 5 pi over 8. Next one gives us 13 pi over 8. And then likewise here, if I add pi to that, we'll be at 15 pi over 8. And then the next one will be bigger than 16 pi over 8, which is 2 pi. So we can stop there. Any questions?